Okay. So hello, let's start. Okay, so some reminder. What we discussed? We discussed the universal enveloping algebra, which is attached to any Lie algebra G. G, the ground field is the complex numbers, but it can be any field of characteristic 0. And next we have a symmetric algebra. Symmetric algebra of the vector space G, and the Poincaré-Bergov-Witt theorem, which says, roughly speaking, that these two objects, this algebra non-commutative and this algebra which is commutative, are roughly speaking of the same size. But more precisely, what this means the following claim, that this object, the non-commutative algebra, is filtered. And this is graded. This is graded. And we know by Poincaré-Bergov-Witt that we have a canonical isomorphism. Canonical isomorphism between the graded algebra, which is associated to the filtered algebra, it is isomorphic to this commutative algebra. And even more, there is some very nice and also canonical map, the symmetization map. Symmetization map, which is an isomorphism of vector spaces. And its crucial property is that it is consistent with the G model structure on both objects, which means that we have two representations of our Lie algebras. We have a representation on this space, we have a representation on this space, and our map is an isomorphism of this object as G models. And this is important because this in turn means, so I recall the definition of the action. The action in both cases is given by the adjoint representation, but which has a slightly different meaning in this case and this case. In this case, it is as follows. We have the adjoint representation of the Lie algebra G acting on itself. And this action extends in a canonical way to the symmetric algebra. On the other hand, in this space, we also have an action of the Lie algebra, which is simply the commutator, taking commutator. Okay. But actually, we have something more. So the next topic is, I would like to briefly discuss it. It is the Poisson algebra structure. structure on the symmetric algebra. What does this mean? A general picture is as follows. So assume A is a filtered algebra. So this is the union of an ascending sequence of vector spaces, and with which is compatible with multiplication, as I explained before. And then we have the graded algebra, and which is also an algebra. And assume that this algebra is commutative. Assume the graded algebra is commutative. What does it, and this just happens in our situation when A is a universal envelope algebra. But more generally, what does this mean? If you take this, means the following. So assume A is an element of some subspaces and B is an element of another subspace. And we assume the commutativity just means if you take the commutator AB minus BA, which in general, it belongs to this subspace. But actually, it lives in this subspace. So AB minus BA equals 0 modulo. And this just means that the graded algebra is commutative. But nevertheless, one can take as element of this subspace modulo this one. And this gives us some operation. This produces some operation which is denoted as follows. An operation on the graded object. I'm sorry, here in this situation, A and B are viewed as element of a graded algebra. Maybe it's better to write as follows. These are top degree terms, meaning that this, informally, this means A modulo. This operation is skew-symmetric. And it satisfies the axioms of a Poisson algebra. What does this mean, a Poisson algebra? Consists of two structures, commutative associative algebra plus Lie algebra. So this is, so I assume that we have some commutative algebra and the operation, the bracket, which makes it a Lie algebra. And these two structures must be compatible plus axiom of compatibility. Which means that we have the Leibniz rule. Leibniz rule, which means as follows: if you have we want to compute the bracket between one element and the product, we can do it by using the Leibniz rule as follows. And this just happens in our situation. One can verify when the graded algebra, which is associated to filtered algebra, and if it is commutative, then it follows that it is algebra with respect to the bracket, which is defined as I tried to explain. And this is exactly the situation for universal enveloping algebra. So it provides that symmetric algebra is a Poisson. What is this? What is the bracket? It's very simple because we have coincide on G with the Lie bracket, and it is extended to the whole symmetric algebra by using the Leibniz rule, because the symmetric algebra is generated by the space G. And a complement to our claim is as follows: the symmetization map okay, no, let's stop at this moment. I'm sorry. Let's stop at this moment. No, I would like to mention the following. The center. Center in and so what does this? Of course, the center here is the center of the non-commutative algebra. So it's clear what this is. What I mean by the center here? The center in is the Poisson. Which means that it is a set of elements such that this bracket is 0 for any y . And now the claim is as follows. The symmetization map produces a vector space vector space, isomorphism. Between so what is this? So this is the center, a set of invariants of the Lie algebra, that is because an element of the universal undeveloped algebra is central if it commutes with any other elements. But this exactly means that it should, it's enough to say that it commutes with G, element of G. So this is the center. So this is the center. And what is here? This is the Poisson center, because this is the subspace of elements which, so what is this? By the very definition, this is this set of elements such that but exactly the same as saying that for any G, and this is exactly the same as set. Okay. So this is the subspace of G invariants in this space. G invariants, but invariants with respect to the action of a Lie algebra just means that the at operator, the corresponding operator, acts as 0. Okay. Some questions maybe. Is it clear or not? Please ask if something is clear or not completely clear. Please ask. Okay. So my goal is to discuss, understand the structure of the center, and describe it in the particular case of the general linear Lie algebra. But first of all, as the first step in the direction of this goal, let's try to understand first. Try to understand what is this space. How to describe it? Okay, I can state the result. The first formulation is as follows. The Poisson center is isomorphic to the algebra of symmetric polynomials in n variables. So take the algebra of polynomials in n variables. There is a natural action of a symmetric group by permutations of the variables, and the invariance, this is my notation for the subalgebra of invariance. And I claim that there is some natural way to establish an isomorphism between this commutative algebra and this commutative algebra. And first of all, what is the structure of this object? My notation is, this is canonical notation. Let X, this X, denote the whole collections of these variables. And this is my notation for the power sum polynomial. There is a classical result that this is a symmetric polynomial, it's clear. And the result is the classical result. Is that the algebra of symmetric polynomials I will denote it follows, is freely generated as a commutative algebra, of course, by the first capital N power sums. So in particular, it is isomorphic to the ring of polynomials, also in n variables. But the difference is that here all generators are degree 1, but here the degree is 1, 2, 3, up to n. So if you want to look at degree, this is not exactly the same as the ring of polynomials, because the degree is defined in a different way. So I will use this result. I hope that we know it. If not, we can, you can look at some textbook to find it. So now what I want to do, I want to find an LX of power sums in this algebra. And so I want to construct an LX I'm sorry, G is G11. How to do this? I recall that we have a natural basis in our GLN algebra, which consists of matrix units. Basis. Matrix units. And I want to define the following elements. Some multiple sum, capital N indices ranging from 1 to n. This is the definition. So in particular, what we have. The first element is just the sum of a diagonal matrix units. The second It can be written as sum over I and j.
I'm sorry, I have a question about the definition of En. I think you misused the notation because we need n, small n somewhere in the definition.
Thank you, thank you, thank you. Thank you. You are right. I'm sorry. Yes, exactly. Thank you. So in this case, what we have this is a quadratic element, quadratic central element, and so on. And so on. And so what I want to prove, prove first, these elements are in the center. I will write in the center with respect to the Poisson structure, and they, no, it's the first are free in the commutative sense. That means algebraically independent generator of the center. So how to prove this? The first claim, so this is size.
I'm sorry, and when you mean the center, you mean the Poisson center of
Yes.
symmetric, yes?
Yes, exactly. So prove this directly by using the Leibniz rule. This is possible. But I want to present another proof of this claim and the second claim, and how to do this. The idea is very important, very important. The idea is to define the following object. This is the matrix n by n, capital N. Matrix composed from the matrix units. So this is the matrix, which is defined as follows. So the first possible question is, what is this? What is this? It can be precisely defined as an element of the following algebra. Let me just, G is GL, to simplify the notation. So one can take the tensor product with this algebra. This is one possible interpretation, and this is exactly the same as the set of matrices with values in this commutative algebra. So this is some rigorous explanation of what is this. Now I claim, and this is obvious from the very definition, that, well, our element is nothing else as the trace of this matrix raised to power n. This follows from the very definition. Look at this, and you understand immediately that this is a trace. Okay. And what next? How to see that it is central, and moreover, that we have a complete description of our center. The idea is as follows. It is very useful to pass from the G invariant, Lie algebra invariants, to Lie group invariants. So assume, let's consider the group G, capital G, which is the general linear group. This is a Lie group, a complex Lie group. So assume that we have, assume V is a finite dimensional capital G mod. What this means? It means that our group acts by linear transformations on a finite dimensional complex vector space, and this action is complex analytic. Of course, we have to know some fundamentals of Lie group, Lie algebra theory, and then it follows that V is also a G model, Lie algebra model. And these two structures, or in other words, a representation of Lie group and a representation of Lie algebra, are related in a simple way. So if you want, for instance, so assume that V, small v is a vector, and X is an element of Lie algebra. What means, so what is the result of applying our Lie algebra element to our vector? It is the same as taking the group element, take the exponential of Tx. T is a complex number, so this is a group element. Apply it to V and take the derivative. The derivative, this is a nice complex analytic vector function. It can be differentiated. Take it t equal to 0. Or what is this, which is the same, one can expand this object, this vector function. It is analytic. We can expand it into a Taylor series in T, and just take the coefficient in T of degree, the coefficient of T in degree 1. So this is the correspondence between these two actions. And so what I want to say, I want to say that the invariance with respect to Lie group is the same as the invariance with respect to Lie algebra. So the invariance with respect to Lie algebra means the subspace of vectors which are annihilated by all elements of Lie algebra. And this is exactly the same as being fixed by any element of a group. So the idea is quite easy. What is essential here? It's important to note that our group is connected, because what we have, one can consider a vector valued function, fix a vector v, and consider this function. So this is a vector valued function, vector valued function on our group G. It is analytic. And the fact that our vector is invariant just means that this function is constant. So this just means that f is constant. And what means that V is invariant with respect to the algebra. This means that this function is annihilated by any vector field on our group which comes from G. Because our algebra is represented by, say, left invariant vector fields. But because our group is connected, these two properties are completely equivalent. So this explains why we have this equality. Okay. So now it's convenient to pass to group invariance. So what next? The idea is to realize our symmetric algebra is the algebra of polynomials on the set of matrices, which is the same as polynomials actually on G star. How to do this? We just interpret, just any matrix units as a function, a linear function on the matrices, which assigns to our matrix its IG entry. And that's all. Okay. And now what we have, the group G, GLN, acts on G by conjugations. This is the capital adjoint representation. And hence it acts on S of G and it also acts on the space of polynomials. The difference is only if you take, in one case here, if you take here the action given by G. In this case, it will be now a little bit different actions. G has to be replaced by G transposed -1, the dual action. But this does not affect the definition of invariance. I could say it in a little bit another way. the action on G and the action of G star the dual space, differ by an exterior automorphism of our group G, which sends an element to G transposed minus 1. But for the definition of the invariance, there is no difference, does not matter. So what this means? This means that this means that under the map, the identification polynomials, you have invariance here is the same as invariant polynomials. So what is the result of this discussion? We consider the action by conjugation of our general linear group on the space of matrices. We have an action of this group on the metric space. If you have some matrix, we just can conjugate it by an element. And we want to understand what are the polynomial invariants. And I claim that this space is generated by the polynomials why it is. But first of all, these polynomials are invariant with respect to our action, which is clear, evident, absolutely evident, because this expression is invariant with respect to conjugation of x for any small n. And next we have to prove two claims. First of all, that they generate this algebra and they are algebraically independent. But now let's restrict to diagonal matrices. But when we get exactly, the nth power sum. Of course, because if we have a diagonal matrix, the trace of this power is this one. Okay. And what next? What we know that these elements are algebraically independent as functions of the eigenvalues. Then it implies that these elements, the first capital N, are algebraically independent. Next, if you have arbitrary polynomial invariant, then its restriction to the diagonal matrix is a polynomial which should be symmetric. Why? Because just look at the action of the permutation matrices. We have the symmetric, our symmetric group is can be treated as the subgroup of GLN, which permutes the vectors, the basis vectors. And this implies that we get symmetric polynomials, or one can say symmetric polynomials in eigenvalues. And the final claim is that if you know our polynomial on the diagonal matrix, on diagonal matrices, then we know it completely. This holds because finally use that generic matrices conjugate to diagonal. So this is the end of the proof of what? Of my claim. Of this one. Okay, is it clear? Some questions maybe? Okay. Now, I want to discuss the center of the non-commutative algebra. G is my shorthand notation for GL. So what I know, this is a filtered algebra. Filtered algebra, as the whole algebra is filtered. And moreover, the graded algebra is our Poisson center, which we know already. And so this algebra as a vector space, not as an algebra, but as a vector space, it's the same, more or less, as this one. And moreover, we even have some explicit isomorphism, the symmetrization. This is a linear isomorphism. And this means that we can take this element and we get some central elements of a center. And even more, if you take first capital N elements, which we constructed, we get generators, free generators of this algebra. This is already a good result. The idea is that to prove that if you have some homogeneous generators here, on the left. And we have, and if you take any liftings of these elements here, what means lifting? Some elements on the right, such that their top degree terms are our initial. Then we get, again, free, in the commutative sense, free generators on the right. So this could seem some good idea, but it's not very nice as a construction. It's not very nice for some reasons. Why? Because it's rather, first of all, it's rather complicated. Already the definition of these elements is not completely simple, because we have some multiple sum. But if you want to get to construct, to use this construction, we have some extra complication, because we have to symmetrize them. It's not a good operation. There are some deeper reasons why it's not a good construction. But fortunately, we can provide a better construction, which actually is, in fact, the same. What means the same? I want now to define the element similar. Similar. And one could use some different notation, but I don't want to simplify the notation. In the center. And the definition is exactly the same. The definition is exactly the same. Which means that the difference with the product is understood in the untitled algebra and not in the symmetric algebra. So the product is a non-commutative product. So now what I want to prove, what I want to claim, that is in the center. And once it's established, it's already easy to see that free generators in commutative sense, which means algebraically independent generators of the center. The same argument using the top degree terms, which enables us to pass from filtered algebra to graded algebra. And because this is because the top degree term of this as an element of universal is the same as an element of a symmetric algebra. I use the same notation for different objects. So now we have to prove what is non-evident. The non-evident is why these elements are in the center. The top degree components are in the center of the symmetric algebra, but this does not mean that these elements themselves are also central, but one can prove this. So, lemma this is my shorthand notation for the center of the universal enveloping algebra. How to prove this result? The idea is we have to consider some more general, which I denote as follows. This is the following. Again, we take the sum. Say, maybe I will use some little bit different notation. Capital N minus 1 indices ranging from 1 to capital N, and the following.
I'm sorry, again, is it small n or big N? Alpha 1, alpha n minus 1, I mean.
Yes, you are right. Again, this is small n. Thank you. And this is the same as taking, again, our matrix, but understood.
I'm sorry, again, it's y, I mean, it's I should be on the first, not I1. So we have I in the start and G in the end, yes?
Mm-hmm. It's okay?
Yes.
Thank you. So let's consider again the same matrix, but we regard it as an element of this tensor product algebra, or which is the same as matrices of order n with entries in this non-commutative algebra. And the definition is exactly the same. So this is again same object. And now I want to observe that this element is simply the following. We take this product, which is well defined, no problem, and the ij entry of it. So this is exactly the same as this definition. Okay. Now my claim is as follows. Fix and then the elements where I and j are as before, they transform under the adjoint representation. So in the same way, as the matrix units themselves. So this means that we have the following. Take the commutator. The result is the same as in the case when n, this n is equal to 1. So the result should be the same, meaning that we have two terms. One is this Kronecker minus this is an exercise. Prove this. It's easy to do by induction. Prove by induction. So the base of induction is n equal to 1, and this is, then we get exactly the commutation, the relations for the matrix units. And in the general case, one can argue by induction. And because of this, we have that sum is central, just as so this is the end of the proof. So I would like to emphasize some point. In order to prove something about these elements, it is very useful to enlarge our construction and look at more general elements of this kind. So now we understand something about the structure of a center. So what is some conclusion? Know that we have. So we have constructed explicitly elements in the center. And we know that the first capital N are algebraically independent generators of Z. Why it's interesting? To understand the reason of the usefulness of this claim, we have to look at representations. So some digression on representations. Representations of this Lie algebra. What kind of representations I want to consider? I will sometimes speak about representations, sometimes of G models, and these two languages are equivalent. So first of all, I want to say what is a weight model. over G. The Lie algebra GLN as any reductive Lie algebra of an algebraically closed field has a triangular structure. Structure which can be written as follows: n minus Cartan subalgebra, the Cartan subalgebra, and n plus. Here, in this case, all is absolutely explicit. So what is this? We have the basis of matrix units, and we have n minus is the linear span of the matrix units such that I is strictly greater than j. So these are the strictly lower triangular matrices. Something below the diagonal and 0 on the diagonal and above the diagonal. And plus is defined in a similar way with I less than j. And finally, the Cartan subalgebra. This is the diagonal matrices. This is or the linear span of the diagonal matrix units. So an obvious decomposition. Of course, this is not a direct sum of Lie algebras. It's a direct sum of vector spaces. All of these objects is a Lie subalgebras, but they are interrelated because, for instance, if you take a commutator of something here and something here, we get an element which is somewhere. It can be, for instance, it can lie in H. It depends. So it's not a direct sum of Lie algebra. And this is a commutative Lie algebra because these elements pairwise commute. Commutators are 0. And what is a weight module? Weight module just means that our model weight V means that V is a direct sum and mu this is a weight, which means that mu is an n-tuple of complex numbers. And this subspace is defined as follows. Subspace of vectors such that when we apply an element of a Cartan subalgebra to V, it is an eigenvectors with this eigenvalue. So the condition imposed on our model is that it is a direct sum of subspaces which are common eigensubspaces with respect to the action of this commutative Lie algebra. So examples. A tautological model. our Lie algebra acts on the n-dimensional vector space in the most natural way. More generally, we can take any tensor space. Also, we can take the dual action, dual model. Let's define it. Let's note it something like this. The action of the Lie algebra on the dual vector space. And again, one can take tensor product, and more generally, we can take mixed tensors. And all these objects are finite dimensional and weight models, because in each case, the natural basis of these spaces, which are obtained from the basis vectors in this space, are eigenvectors, which is pretty obvious. And for instance, some other example is as follows. We can take, say, universal envelope algebra and the adjoint representation of G. So our G acts on itself by taking the commutator, and there is a natural extension of this action to the universal algebra. For instance, by taking commutators, again, one interpretation, and again, we have this module. It's infinite dimensional, but this does not matter. Again, one can produce a basis which consists of weight elements. Okay. The next, what I want to, there is some order. What I want to, some no, what I want to say is the following. So assume V is a weight model we say V is the highest if there exists a vector V, which is called the highest weight vector, such that two properties. First of all, V is annihilated by n plus, which means that if we apply, we get 0. Okay? And it is a weight vector, so we assume that V for some mu in general and tuple of complex numbers. And the third properties is V is cyclic, which means so that if you apply the whole algebra to V, and we get the whole space. In other words, the minimal invariant subspace generated by our vectors is the whole space. And there is a whole theory of such models. For instance, examples. Any irreducible finite dimensional G model. Next, there is some, in a certain case, in a certain sense, universal highest weight models, which are called Fermat models. We don't need to understand completely what I'm trying to say, because this is just a preparation to some result which I want to say today and prove on the next lecture. So maybe I will skip some details. There is an easy claim, I have no time to prove it. I want just to state it. Easy claim. So assume that V is highest weight G model and of highest weight some lambda, which does mean that there exists a vector with the properties as I listed above, only with mu replaced by lambda. So maybe I will repeat it. So it is annihilated by n plus and cyclic. Then any central element, say A, acts on V as a scalar. So the image of a center in the set of operators on our vector space consists of scalar operators. So this is a kind of Schur lemma. This is a kind of Schur. This means what we have, this means given highest weight model, for instance, an irreducible representation of our algebra, say V, and lambda is the highest weight, we have a homomorphism of a center to the complex numbers, say phi. And the problem that I want to study, is the following. Given lambda, compute it turns out that the result does not depend on the model, because it may happen that there are several highest weight models with the same highest weight lambda. But the result does not depend. It depends only on the weight lambda. So the result I want to produce, to explain, is how to compute this. And this was given by the theorem due to two mathematical physicists, Perelomov and Popov. In the 60s, this is an old result, which I think is very important, very nice. Very nice, and now I want to stay it. And I will prove it later, but I want to. So my notation is as follows. So if you fix this element, we get some function on the set of weights, or simply on this vector space, some function. It turns out that this function is some polynomial of degree which is equal to n, and the Perelomov-Popov theorem computes in a certain way, a little bit complicated, what is exactly this polynomial. And the result can be stated as follows. It can be stated in different ways, and I want to state it in terms of generating functions. So the result is as follows. Let me write it. So this is our eigenvalue to compute. Now let's take the generating function. And on the right, you get the following. I have to explain what are these quantities. Where this is the notation. So this is a nice result. I will explain why it's important, why it's nice. It's non-trivial, some non-trivial computation, which will be given in the next lecture. But I would like only to state a problem exercise. Deduce from this equality that these functions are symmetric polynomials in these variables, in these shifted variables, shifted coordinates. These are natural coordinates, initial coordinates, and these are shifted coordinates. And moreover, these are symmetric polynomials of the following kind. Plus lower degree terms. So this is, in a certain way, something similar to the P sub n function, the power sum function. But this is some non-commutative, in a sense, a non-commutative version. So this is the end. I will prove. Next, I want to prove this formula. Okay. So let me stop.